Hi, everybody. This is the overview lecture to go along with assignment 20. This is the title of this is the Gauss-Jordan method for dealing with systems of linear equations. Before we actually launch into whatever that means, Gauss is a pretty famous mathematician, and he did do some pretty cool stuff. So we're going to learn this technique that he developed, but why? Right? Why do we want to do it? Let me try to explain the why first. Basically, last time we saw one of the uses you can put a matrix to is to represent a system of equations. So I want to kind of rehash that and then give you some extra terminology about it. But this is the system I think the very first one we looked at in the overview lecture, where the sum of two numbers is 38 and the difference is 6, and we were able to solve that by a multitude of ways. But that thing can also be turned into a matrix, and then what's cool is you can unleash the Gauss-Jordan method on it, and you can also do it if the matrix is considerably more complicated, something that we wouldn't be able to solve easily by hand. And you'll get an answer. That is, you'll find values for all of the variables in the equations you've got. That doesn't sound that impressive when I've only got x and y, but I could have 13 variables and 13 equations. This matrix could be a 13 by 14 array, and that's not easy to deal with by hand, but a computer will solve it in a microsecond. So we can get practical answers to real world problems that are very complicated using machinery. Well, okay, so let's talk about this matrix. This is known as the augmented matrix of the system. It's typical with an augmented matrix that the right-hand column, the farthest right column, is the stuff on the other side of the equal sign. It's any constants that appeared there, so the 38 and the 6. And this dotted line basically is replacing the equal signs. You don't even need to have that there, but it's sort of conventional. A lot of people like to put that in there because it separates things into two different groups that are kind of, nice to keep separate. The idea basically is the matrix is just the same as the system of equations with all the decorations removed that you don't really need. I mean, do you notice how in both equations I mentioned x first and then y? Well, that means the numbers in the first column of the matrix are going to be whatever goes with x. There's no need to write x if you know that. We just need the ones that are in front of those x's. I know there aren't really ones there, but we can imagine there are. The coefficients that go in front of x go into the first column, and the numbers that are multiplying y go into the second column. Right. Well, I just said coefficients. That's what makes this the first couple of columns before that extra one. That's what leads to the terminology. That's the coefficient matrix. And I'm going to call that A. So we have our augmented matrix, which consists of a coefficient matrix and then an additional column, which is really a vector. That's the stuff on the right-hand side. Another way to look at the system is take that coefficient matrix and multiply it by the variable vector, a vector that has your x's and y's in it, or if there's 3 variables, it would be x, y, and z, etc. So a times xy is being set equal to the thing that's on the right-hand side. So they mention this in the book, but honestly, this version of it is what we'll use most often when we're doing computing. Okay, so what the Gauss-Jordan method does is turns a matrix into one that's called triangular. And I want to show you why we bother with that. If you have a triangular matrix, it's particularly easy to solve it. So first off, this is an example of a triangular matrix, and there's a triangle of zeros in it. I guess that's why they call it triangular. Okay. The stuff below the first one there in the 1, 1 position, that's all zeros, and then there's 2 numbers in the second column, but then there's a 0 under that. A little triangle of zeros. Why is it that I think this is such an easy system to solve? Well, let's write it again as a system, so that we'll take it away from the matrix form and write it as a system. All right, so the version of this turned into a system of equations would be, let's use x, y, and z as the variable names. So the top row corresponds to the equation x plus 2y plus 3z equals 10. The middle row doesn't have an x in it. It's kind of the point of the zeros, that some of the variables are missing from successive rows. Let's see, it would say y minus z equals 1. And the bottom row, x and y are both multiplied by 0, so they disappear. The last row really just is z equals 2. So look how quick this is to solve. You already have that z is 2, and you know that y minus z is 1, so what's y? This is what we're doing, is called back substitution. Z is 2, y minus z is 1. That leads us to y is 3. Right? 3 minus 2, sure, that's 1. Now if z is 2 and y is 3, we can calculate what this stuff is. 3 times 2 is 6. 3 times, that's another 6. X plus 12 equals 10. It looks like x is minus 2. You can really quickly get to the solution if your system has the triangular shape. So what the Gauss-Jordan technique is about is taking arbitrary matrices and putting them into that triangular shape. And you usually can do it. There's a rare situation that happens when the thing won't play out properly, but most of the time you're able to do this and so get a solution. In fact, I guess one way to think of the boundary case there where you can't actually use the technique to get to a solution is, well, you know, there's some systems that don't have solutions. If you have something contradictory in the system, and it may not be obvious that there's something contradictory in the system, but if somehow the equations kind of combine together to give you something that's impossible, then you won't be able to get a solution because there isn't one. So this Gauss-Jordan method will fail then. But for randomly chosen matrices, it always works. Okay, where do we go next? I guess we better start talking about the method. So there are basically 3 operations that you can do to a matrix. I'm going to write them down. There they are. You can, first of all, swap any rows that you like. What does that come down to if you're thinking about the rows as representing equations? It just means you're mentioning the equations in a different order than you originally had them. That's obviously not going to affect the outcome. It's not going to affect the solution. And the point of these operations that we're able to do, and which we're going to use to enact the Gauss-Jordan method, is none of them affect the answer. They are all things that you can do which won't have an impact on what the solution set is. Number 2 is another one that's easy to think about. If you take a row, any row of a matrix, and you multiply everything in that row by some fixed constant number, what is the effect of that? Well, that's like, if in terms of the equations, it's like taking both sides of the equation and multiplying by something. And that's something we know is a valid thing to do from algebra class way back, right? It's always fair to multiply both sides of an equation by the same thing. So you're not going to affect the solution by doing that. The third thing that's mentioned here, I've only told you the name of it. It's called row replacement. And it's the trickier thing. So let me say roughly how it goes. If you have 2 rows, say row K and row J, what row replacement looks like is this. You take row K and you set it equal to itself plus some multiple of the other row, m times row J. We'll actually see that in effect, but what it basically does is combine 2 of the equations. It doesn't lose either of the equation's values, or values in the sense of, that they're useful in finding solutions. And this is the hardest one to justify, that it really doesn't change the solution set. But I think we're just going to take that on faith. This is an operation you can do that won't change a solution set. So here's a matrix that we'll use as an example. I'll point out one of the things that's kind of a pain in the neck when it comes to doing these this Gauss-Jordan technique is that you have to write the entire matrix over and over and over again. It does get boring, so we won't do this a whole lot. We'll do enough of it that you understand how the method runs, and then we're going to take the approach of just let's use a computer to get the actual answer. All right, so what you need to do is basically produce zeros down here below the first one. That's the first step. Make sure you got a 1 in the first position. Now I got lucky on this one. I do have a 1 in the 1, 1 position. If that was something other than 1, I would scale that row by something until that was a 1. And then I'm gonna produce zeros down below. Now, one thing in this particular matrix, I'm just looking at the structure of it. See how we've got a couple of zeros there? You can sort of jump the gun on the process and make this the bottom row. In other words, do a row swap. Now, what I want to do is interchange the second and third rows. So that looks like this. The first row is unchanged. What's now the second row is going to become what was the third row. So 1, 2, 3, and 7 in there. And then what was the second row is going to be into the third position now. Now I'm going to come back to here. I want to create nothing but zeros under here. In fact, wow, my answer is going to be in triangular form as soon as I do that. Here's where we'll need to do the row replacement operation. And what it's going to be, I'll say what it's going to be first. We're going to replace row 2 with itself. The row replacement always reads that way. Replace row whatever with itself plus or minus another row. In this case, we want to subtract off the entries in row 1. What's that going to do? Well, the only purpose for it is to make this entry become a 0. Now, what are we not changing if we do that? Well, we're not changing row 1. So 1, 1, 2, 4, those going to go back in. We're not doing anything with row 3. 3, 0, 0, 2, and 5, stay put. The one thing we're doing is changing row 2 so that it's equal to itself minus the entries in row 1. And those are corresponding entries, right? So 1 minus 1, that gets us a 0 here. 2 minus 1, that makes this a 1. 3 minus 2, that's a 1. And 7 minus 4, that's a 3. And now that's a system that can be solved by back substitution. Technically, to get it into totally the standard form, we'd also like to make that position a 1. We should have this triangle of zeros and then 1s on the diagonal. So let's go ahead and do that, just because I'm showing you this for the first time. We might as well dot the I's, cross the T's. The operation I'm doing now is row scaling, and I'm going to scale row 3 by a factor of 1/2. And so it's going to become 0, 0, 1, and 2.5. Kind of usually prefer to go into the decimals rather than fractions if we're doing it. Now this is in that really nice form where you can figure out the answer. The last equation is literally says z is 2.5. The next one says the sum of y and z is 3. So now I know y is 1/2. Right? I get z is 2.5. Y is 0.5, because the two of them together have to add up to 3. And then what is this going to say? Well, that would be 2 times 2.5, or 5 plus a half. 5.5 plus x gives us 4. X has to be negative 1.5. You see, I could literally do that in my head once I had the matrix in this triangular form, which is kind of the point of all this. So that's a quick overview of the Gauss-Jordan method. You can see it dealt with sort of more rigorously in the textbook, which I encourage you to do. But I think that's a good place for us to stop today. So have a great rest of your day.